Welcome to Visual Spectrum Analysis with Wi-Spy and Chanalyzer. In this webinar, we're going to talk specifically about spectrum analysis and how you can use it to troubleshoot problems with your wireless network or improve the performance of your wireless network. My name is Joel, and I take care of the majority of training and support here at MetaGeek. I'm always assisted by one of our developers or marketing people or somebody else from the company. Every day, we bring in someone from the company to help me with support for a little while. But for the most part, I'm the guy that answers the phone, answers tickets, creates support materials, and teaches webinars like this one. If you'd like to get in touch with me, feel free to open up a support ticket at support.metageek.net. Believe it or not, that actually is the highest interrupt on my list of interrupts. That's the fastest way to get a hold of me. The only faster way might be through Twitter. If you're on Twitter, feel free to contact me there if you have a quick question or something that you'd like to ask, especially if it's not during normal business hours. That's usually a very quick way to get a hold of me. Just a couple of housekeeping things to keep in mind during the course of this webinar. If you have any questions, feel free to use the question tool to ask those questions if it pertains to the content in the webinar. Some dialogue can really make for a great webinar, so feel free to participate in that way if you wish. Also, if you experience any audio or video problems, if the audio is garbled or you can't see the slides or you can't see what I'm doing on the screen, just let me know and I can usually take a quick moment and I can usually fix that problem. So just let me know if you experience any audio or video problems. So with that, let's go ahead and get started. The first thing that I'd like to do is I want to make a comparison of 2.4 and 5 gigahertz. I want to kind of compare the 2.4 and 5 gigahertz band. And this is really important when you're working with Wi-Fi in any capacity. It's very important to understand the fundamental differences between 2.4 and 5 gigahertz. And as we get into spectrum analysis, there's some differences between these two bands that we kind of need to think about. So first, let's talk about the 2.4 gigahertz band. The 2.4 gigahertz band, first off, has a greater range than the 5 gigahertz band. And that's because the 2.4 gigahertz wavelength is longer than the 5 gigahertz wavelength. The 5 gigahertz wavelength is shorter, so it just doesn't go through things nearly as well. It attenuates more. It doesn't punch through things nearly as well as the 2.4 gigahertz band does. So with the 5 gigahertz band, we're going to see a lower indoor range. It's just not going to travel as far indoors. Now, outdoors, 2.4 and 5 gigahertz behave almost exactly the same. Free space path loss is really about the same for both 2.4 and 5 gigahertz. So you're going to see them perform pretty well. But in the 2.4 gigahertz band, you're going to see what most vendors will say is about a 300-foot range. And in the 5 gigahertz band, you'll see about a 90-foot range. Now, of course, this is going to vary a lot depending on your environment and the equipment that you're using, and all sorts of different factors are going to come into play there. But most vendors are going to say about 300 feet versus 90 feet. The next thing to think about when you're looking at the differences between 2.4 and 5 gigahertz is that 2.4 gigahertz is compatible with pretty much all Wi-Fi devices out there. Pretty much every Wi-Fi device is going to cite 802.11b, G, and N support, and those are all 2.4 gigahertz standards. There's really no Wi-Fi devices out there that are single band in the 5 gigahertz range only. Everything is going to support 2.4 gigahertz out of the box. Whereas in 5 gigahertz, things are a little bit different. In the 5 gigahertz band, you kind of have to keep an eye out for devices that support 5 gigahertz. There aren't a whole lot of devices out there that do. If it doesn't say 802.11a, and if it doesn't say 802.11ac on board, then you know that it's a single band device that only supports 2.4 gigahertz. And to really understand why this is, we kind of have to go back in time. We kind of have to have a quick history lesson to really understand why there are less 5 gigahertz devices out there. And it really goes back to 1997 when the IEEE introduced the first 802.11 standard, which was simply called 802.11. It had a maximum data rate of 1 or 2 megabits per second. I don't remember off the top of my head, but it was a slower data rate, like 1 or 2 megabits per second. And it was originally intended for wireless barcode scanners in warehouses. So 802.11 was a 2.4 gigahertz standard that had a slow data rate and was only present in the 2.4 gigahertz band. Fast forward to 1999, and the IEEE introduced two new standards. They introduced 802.11b and 802.11a at the exact same time on the same document. Two separate standards, but introduced on the same document. 802.11a was a 5 gigahertz standard, and 802.11b was a 2.4 gigahertz standard. Now, 802.11b maxed out at 11 megabits per second, But 802.11a had a maximum data rate of 54 megabits per second. So it was 5 times faster. But there were a couple things that kept 802.11a from becoming more prominent. First off, 802.11b devices were cheaper to make because we'd already been doing stuff in the 2.4 gigahertz band for a little while. And it had a better range. It had a much greater range of about 300 feet, whereas 5 gigahertz had that lower indoor range. And since it was in a brand new band, 5 gigahertz, it was a bit more expensive to manufacture. So more expensive to buy, and you had to deploy more equipment to cover a warehouse. Because of that, 802.11a just didn't catch on like 802.11b did. And we're still feeling the results of that today. When you go to the store to buy a device, it's very easy to find a device that cites 802.11b GN support. Now remember, 802.11n can exist in 2.4 gigahertz only, or it can exist in 5 gigahertz. If you see BGN, that means that it's a 2.4 gigahertz only device. If you see 802.11a, then you know that is a dual band device. More and more devices are starting to support 5 gigahertz. Back in 2012, Google released a tablet called the Nexus 7, a 7-inch Android tablet, and it had 802.11b GN support, so single band only, and this was 2 years ago. In 2013, last year, Google refreshed the tablet with the 2013 Nexus 7, and it had 802.11a BGN support. So now it is a dual band device that supports both 2.4 and 5 gigahertz. And pretty much every Apple device that's been released for a long time now, starting with the iPhone 5, has 802.11a BGN support. Every MacBook Air, MacBook Pro, even my old 2009 Mac Mini has a dual band radio on it. But you're still going to see a few devices out there, like inexpensive laptops, maybe some Chromebooks, and some cheap Android phones and tablets like the Moto E and the Moto G don't support 5 gigahertz. So we need to think about that. We need to make sure that we're providing backwards compatibility with our older Wi-Fi devices. Since 2.4 gigahertz has a nice range for Wi-Fi devices, and since it's kind of been the default band for so long now, it's highly congested with Wi-Fi. There's a lot of Wi-Fi devices that operate in the 2.4 gigahertz band. And if the range is good for Wi-Fi, it's good for non-Wi-Fi devices as well. So we see a lot of non-Wi-Fi devices, and they plague the 2.4 gigahertz band with interference. And we're going to talk about that a lot today. Perhaps the worst problem with the 2.4 gigahertz band is that it has only 3 channels that don't overlap. I apologize, my slides keep skipping ahead. My annotation tool works okay, but it's not perfect. We have only 3 non-overlapping channels in the 2.4 gigahertz band. And you might be thinking to yourself, well, hang on a second. Aren't there 11 channels in the 2.4 gigahertz band? At least in the US, don't we have 11 Wi-Fi channels? Well, you're right. We do have 11 Wi-Fi channels, but here's the problem. Each Wi-Fi channel is about 20 megahertz wide. That box there shows where channel 1 is. To find channel 2, we're going to start at the center of channel 1 right there, and we're going to go up 5 megahertz. And that's going to put us right about there. That's about where the center of Wi-Fi channel 2 is. So if we draw a box to show where channel 1 is and we go up 5 megahertz and we draw a box for channel 2, it puts channel 2 right about there. Both channel 1 and channel 2 partially overlap because there isn't enough room for 11 non-overlapping channels. So most of these channels partially overlap. So what you're going to see, and you're going to hear this over and over and over again, is that the only 3 channels that don't overlap are channels 1, 6, and 11. Now, if you're in Europe or in other parts of the world, you have a few more channels available to you, so you can use channels 1, 5, 9, and 13. But for the purpose of this webinar, I'm just going to speak for the US today, and that we have 3 non-overlapping channels, channels 1, 6, and 11. Now, if we look at the 5 gigahertz band, instead of 3 non-overlapping channels, we have 24 non-overlapping channels, 24 channels that do not overlap. The IEEE, when they ratified 802.11a, they realized that this could become a problem, and it definitely has become a problem. So they created 24 non-overlapping channels. Now, each one of these channels is still 20 megahertz wide, just like their 2.4 gigahertz counterparts, but there's so many more of them that I have to draw them more narrow here, and you'll see it represented in that way quite a bit. Because of that and several other factors, we see much greater performance in the 5 gigahertz band. And if you look at the spectrum, and we're going to get into this really in depth, but when you look at the spectrum, which one is busier? The 2.4 gigahertz band is very, very busy, whereas the 5 gigahertz band isn't very busy at all. And from what we've seen, this is really, really common. It's very, very common to see that 2.4 gigahertz is overutilized, whereas 5 gigahertz is underutilized. And we need to make sure that we're utilizing the 5 gigahertz band in that way. The next thing that we want to talk about as we're kind of leading up to spectrum analysis is the half duplex nature of Wi-Fi. Now, many of you are familiar with an Ethernet cable. An Ethernet cable has got multiple twisted pairs of copper in one cable, so we can send traffic in two directions at the same time. It's kind of like a two-lane highway. We can send traffic east and west simultaneously, thanks to those multiple lanes of traffic. But with Wi-Fi, things are a little bit different. With Wi-Fi, we have one lane of traffic. When two Wi-Fi devices are communicating with each other, they're going to be on the same channel, and only one device can talk on that channel at any given time. If they both try to talk at the same time, their communications are simply going to collide and they're going to cancel each other out. It's a lot like having a conversation with a friend. If you're having a conversation with somebody and you both say something at the exact same time, you're going to interrupt each other. You're going to cancel each other out. Your friend's not going to understand what you said, and you're not going to understand what your friend said. It's much the same with Wi-Fi. So Wi-Fi has a process to take care of that problem, and it's a process of data and acknowledgement. Let's say that this iPad has a data frame that it needs to send to this access point. It's going to start by transmitting a data frame. It's going to send that data frame to the access point, and the access point is going to go, yep, check, I received that data frame, and it's going to reply with an ACK or an acknowledgement. It's going to acknowledge that it received that data frame. Now, there's a few things that can go wrong here. Let's say that for whatever reason, the signal just doesn't make it to the access point. Maybe the access point is a little too far away, or maybe there was some interference, and so the transmission got garbled or something like that. And for whatever reason, it just didn't make it to the access point. The client's going to listen for a moment and it's going to go, okay, well, I never heard a response, so maybe the access point didn't receive the frame. So it's going to send the data frame again, and it's going to send the data frame again, and it's going to keep resending that frame until finally the frame makes it through and the access point acknowledges that frame. This is called a retransmission, and we want to avoid those as much as possible because that's repeating ourselves. We want to have quick, clean, and efficient conversations. Now, this is a nice example, one client, one access point, but we all know it's really not like that. In the real world, it's going to look more like this. And even this isn't quite complex enough. Even this isn't really what it's going to look like. It's going to be more complicated than this. But in this example, we have 6 iPads and one access point. And while iPad number 4 is sending a data frame to the access point, all of these other devices need to be quiet. They all need to be quiet and wait for their turn to talk, even the access point. If any of them try to talk right now, they are going to interrupt that transmission, like this unknown device right here. Now, we don't know specifically what this device is, but to be honest with you, it doesn't really matter. It's anything on the same channel or the same frequency that tries to talk at the same time and interrupts that transmission. This can be a cordless phone. This could be another Wi-Fi device that doesn't know there's a conversation happening right now. This could be a microwave oven. It can be anything on the same channel or on the same frequency that's in range of this wireless device, and it can block that transmission. So we want to avoid that. So let's look at different types of interference. We've been talking about co-channel interference already. This is where we've got a whole bunch of wireless devices and a whole bunch of access points and devices all on the same channel, and they are all going to compete for time to talk. They're going to take turns talking because only one device can talk at a time. And we touched on adjacent channel very, very briefly earlier. We talked about adjacent channel for just a moment. This is where we have networks and devices on partially overlapping channels. So we've got a network on channel 4, a network on channel 6, and a network on channel 5. If you remember, in the US, the 3 non-overlapping channels are 1, 6, and 11. In Europe, it's 1, 5, 9, and 13. These 3 channels all partially overlap. If we were to draw a box to show there's where channel 6 would be, and then here's where channel 5 would be, and then here's where channel 4 would be. All 3 of these channels partially overlap. And so instead of taking turns talking politely like we do with co-channel interference, these 3 networks and all the devices on them are just going to yell over each other. They're just going to scream over each other. And it's a lot like a conversation at a restaurant. If you're at a restaurant and you have a table with some friends, you're all taking turns talking politely, much like co-channel interference. There's a high possibility that a group of people is going to get a table next to you. Now, they're not a part of your conversations, but you can still hear them, much like these devices can hear each other. But instead of taking turns talking politely, you're not going to take turns talking with their table. They're just going to have their conversation, and you're going to have your conversation, but you can still hear them. So to compensate, you might talk a bit louder, and to compensate, they might talk a little bit louder until everyone at each table is saying, "What? I'm sorry, I couldn't hear you. Can you speak up a little louder? Can you repeat yourself? Because I wasn't able to understand you because of the table next to us making all of the noise." That's a lot like what adjacent channel interference is. And we want to avoid this at all costs by using channels 1, 6, and 11. If we could have everyone in the world adhere to that, either 1, 6, or 11, or 1, 5, 9, 13, the 2.4 gigahertz band, Wi-Fi in the 2.4 gigahertz band would work better for everyone. So spread the word. Let's make sure that everyone's educated about that. Finally, the primary topic of conversation today is non-Wi-Fi interference. This is activity from non-Wi-Fi devices like cordless phones, Bluetooth devices, wireless mice and keyboards, all of those devices that talk in the 2.4 gigahertz band. Non-802.11 devices are also going to compete for time to talk. And typically, they aren't nearly as polite as other Wi-Fi devices. So different tools for different jobs. Insider is our Wi-Fi scanning tool, and it can use your wireless adapter to listen for wireless networks. So we can go, oh, hey, we know there's a network on channel 1, and we know there's a network on channel 2, and that network on channel 2 is going to cause adjacent channel interference. We should fix that. Let's move it to a different channel, or let's fix that problem. You can use Insider to fix that problem because it scans for wireless networks, and it can hear all the wireless networks around you. But Chanalyzer and a Wi-Spy are very special in that they can hear more than just the Wi-Fi networks like Insider can. Not only can they hear the Wi-Fi networks from your wireless adapter on your computer, but they can hear the non-Wi-Fi devices as well. They can hear the devices that aren't speaking Wi-Fi. They can hear the devices like cordless phones or microwave ovens and all those things that generate activity in the 2.4 gigahertz band. Basically, Wi-Spy plus Chanalyzer, since they're a spectrum analysis solution, can hear any raw radio frequency activity in the band. And we can use that for several things. We can check to see how busy a channel is. We can see there's a little bit of activity on that channel, but you know what I'm really worried about? We can see that there is a non-Wi-Fi device talking constantly here, and that's going to be a problem. And Keith, your question, will there be a recording shared afterwards? I actually am recording this webinar. So after the webinar, feel free to email me at support@metageek.net or open up a support ticket. I'll give that information at the end of the webinar and ask for a copy of the webinar. I'd be more than happy to send that to you. So we can use Chanalyzer and a Wi-Spy to find these sources of interference. And there's a few things that we can do with this. We can maybe move our wireless network down to a different channel, or maybe we can move our non-Wi-Fi device to a different channel, or maybe we can just unplug it and get rid of it, which to be honest is usually the solution for old analog devices that might cause interference. What we're seeing here in this screenshot, this is a screenshot taken with Wi-Spy and Chanalyzer. We can see that our wireless card is detecting a Wi-Fi network right here on channel 5. Not sure why we put it on channel 5. Obviously, for the sake of example, don't do that. Unless you're in the UK or somewhere in Europe, then that's fine. But what we can see is that this is where our network is, and we can see that there is a non-Wi-Fi device causing interference, and that's going to keep our Wi-Fi devices from talking on that channel. It's going to interfere with our wireless network. And because we have a Wi-Spy, because we have Chanalyzer, we can actually get visibility into that because we've never been able to see that before. So one thing I want to talk about really quick is the time domain versus the frequency domain. Basically, the difference between an oscilloscope and the difference between a spectrum analyzer, which is on the right. Some of you may wonder, why are we using a spectrum analyzer instead of an oscilloscope? Well, it all comes down to which domain we are looking at. With an oscilloscope, we get to see amplitude, and we get to see how often things are happening on the frequency that we have selected. With a spectrum analyzer, we get to see something different. We get to see the amplitude, how loud things are talking. We get to see the frequency or the channel that it's talking on. So we get to see that specifically. And with our spectrum analyzer and a few others out there as well, we also get to see things talking over time. So it gives us an extra dimension to look at. And that's why we are looking, that's why we're going to look at something with a spectrum analyzer instead of an oscilloscope. So what does spectrum analysis look like? Well, Like I mentioned, we get to see the amplitude. We get to see how loud something is talking. We can see that there's something talking loud here, but it's not nearly as noisy over here. So that's what we get to see. The height of the graph tells us how loud something is talking. We also get to see where it's talking, whether that be a channel or frequency, which are really just the same thing, just different labels. So not only do we get to see how loud things are talking, we get to see where they're talking. Does anyone remember Winamp? I used to use a tool called Winamp, which was an MP3 playback tool. Back in the heyday of MP3s and things like that, Winamp was an MP3 playback tool for Windows, so you could listen to music with it. You could build playlists and do all that complicated stuff. And it had an audio visualizer in it. It had a tool that you could visualize the audio with. And as you ran the audio visualizer, you could see if there were high notes being played, you would see spikes towards the top. And if there were low notes being played, you would see spikes down towards the bottom. An audio visualizer and a spectrum analyzer really are pretty much the same thing. They really analyze pretty much the same thing, but instead of looking at audio, we're looking at radio frequency. Here's where the high notes would be played, and here's where the low notes being played. Or maybe you could say, here's where the high frequency things are, and here's where the lower frequency things are. So we can look and see several different things. We can see how loud things are talking, and we can see where in the band they are talking. And with Chanalyzer, we've actually got a unique way of visualizing something else. Not only do we show you how loud things are talking and where they're talking, we also can show you how often things are talking. And we do that with color. We call this color by utilization. So here we've got some blue spikes. And those blue spikes are telling us that, yeah, there's some activity here, but it's very, very infrequent. It's not happening very often. Whereas these green shapes here are saying, hey, there's something talking here a little bit more often. It's still not super often, but it's definitely more often than the blue spikes. A blue spike tells us that something is happening there pretty infrequently. A green shape is showing us that something's happening there about 20% of the time. And then if we saw yellow or if we saw red, that would indicate that something is talking there much more often. We'll go over that a little bit more in the live demo. Speaking of live demo, slides are kind of boring, so let's get out of them and let's take an actual look at the software. I'm just going to switch to my Windows virtual machine. And let's go ahead and start up Chanalyzer. And what I've done here, since I'm presenting from, this is just my MacBook Air. This is the primary display on my MacBook Air, 1366 by 768. This is pretty much the lowest resolution you should see on a modern laptop. And I've just got a Windows 8 virtual machine here, and I've got a USB Wi-Fi adapter connected to this so that I can get my Wi-Fi data into the virtual machine. And I've got my Wi-Spy DBX connected to that virtual machine as well. So I'm going to start by clicking View and hiding the Session Manager. Let's just concentrate on the main bit of data that we're looking at here in Chanalyzer. So let's start by looking at this top pane here, which is called the Density View. Like I said earlier, the density view shows us what's happening over a period of time. If we get rid of density, we can see that we've got this blue line here moving around, and this is showing us what is happening in the spectrum right now. This is the raw radio frequency activity that we can see in the 2.4 gigahertz band. If we want to switch our labels from Wi-Fi channels to frequency labels, we can do that. So now we're looking at the frequencies, but since we're working on Wi-Fi today, I'm going to switch back to the Wi-Fi labels. So we can see what's happening in the band right now. We can see there's some stuff talking, but I don't know about you, but I have a really hard time keeping track of that. It's really difficult for me to keep track of that. Now, you can use an average trace to see what's going on. You can also use a max hold to see what our maximum amplitudes are on any given frequency, but I like to use color by density. So like I said earlier, the intensity of the color shows you how often something is occurring there. We can see a bunch of blue spikes, which indicates that there's some activity there, but it's happening less than 10% of the time. It's not happening very often. We can see a bit of green here, and that green indicates that there's something happening there about 20% of the time, not super often. If we saw a yellow spike, then we would know something is talking about 40% of the time, and red means that something is talking at least 50% of the time. We want to make sure that we don't have any devices that are hogging up all of the time to talk. We don't want devices to hog up time to talk. So let's take a look at an example of an interfering device. I'm going to turn on a device that's going to cause interference, and let's take a look at what that might look like. So very quickly here, you're going to notice that we've got this spike that showed up in the spectrum. What's going on there? What's up with that spike? And if we enable density, we're going to notice that over time, this spike is going to turn from blue, and then eventually it'll turn green, and then it'll turn red. Eventually it'll turn red, because this spike is holding there constantly. It is talking constantly, and we want to keep a close eye on that and what is going on. You'll also notice that there's a view down here below called the waterfall view, and the waterfall view shows us what's happened over a period of time. But instead of the color telling us how often something is talking, the color shows us amplitude. So notice the high point of this shape is the most red point. This is the highest amplitude point. And notice that those two line up perfectly. We can see here where it started talking, and we can see that it is talking constantly. And the waterfall view flows from top to bottom, just like a real waterfall. So we can see that this device is talking constantly. It's a non-relenting signal. In fact, it is dark red because it is talking so often. If we want to see exactly how often it's talking, we can visit the utilization graph here, and we can check and we can change at what amplitude point we want to measure utilization. And let's check it at negative 60 dBm. So this line right here. So let's change this to negative 60. We can see that between channels 5 and 6, we can see that this is talking 100% of the time. It is talking constantly. And so this is going to bar any Wi-Fi devices from talking. Anything on channel 1, channel 5, even all the way up to channel 9, probably isn't going to get an opportunity to talk, because this device is talking constantly. So let's say that we want to track this device down. Let's say that we go, okay, this is a problem. This is interfering with my wireless network. If we enable our networks view here, at this point, we can't even see the MetaGeek networks anymore, because this device is talking so often. I am knocking out the Wi-Fi for everybody in the 2.4 gigahertz band right now, at least everybody on channels 1 through 6. So let's track this device down. So to do that, what I can do is I can click and drag sideways on this device and release the mouse button and click Device Finder. Let's clean up our selection a little bit, and then we'll hit the checkbox to start Device Finder mode. This is a special mode where we're only sweeping this little narrow band, and we're looking at a signal strength graph for this device. Now, obviously, I'm sitting at my desk right now. I'm not moving around, so I'm going to simulate moving around. But what we can see here is that when the signal strength drops, we know that we've moved further away from our device. But if the signal strength goes up, we know we're getting closer. And if we see that signal strength go back down again, we might go, okay, we're going in the wrong way. We need to turn around and go back to where the signal strength was the highest. Until eventually we might end up in the same room with this device, at which point we'll see the signal strength peak. And if we see red on this little bar over here, then we know that that signal strength has fallen. We can see the high mark. Where were we at the high mark during this process? And as soon as I disconnect this device, we see the signal strength fall to the floor. Device Finder is kind of a two-part thing. It's not only a feature in Chanalyzer that you can use with an omnidirectional antenna. We also offer a highly tuned directional antenna called Device Finder that works with this feature directly. And for the best results, you can use the Device Finder, because now it gives you some directionality, kind of like a flashlight as you're looking around to find that device. So now that we found this device, let's go ahead and exit Device Finder mode, and that'll kick us back out into the main mode. Now, the next thing that you may have noticed is we've got this waterfall view in the center here, right? And it's showing us what's happening over time. We've got the data going from the top down here to the bottom. You may have noticed that there's an identical waterfall view over here, except this waterfall view is a lot more stretched out right now. That's because the waterfall view over here is called the navigation waterfall, and it shows us the entire recording from start at the bottom to finish, or what's happening now. You can see that as we're adding sweep data, we're adding that to the top of our waterfall view, and we're slowly putting more and more and more data into the waterfall view. The neat thing about the waterfall view is, like I said, this is start to finish on our recording. And at any time, we can pause the recording. And notice what Chanalyzer does. It's still recording data in the background. It's adding more data to our waterfall view. And so whenever we want, we can hit play. And now think of it kind of like a DVR. We're lagged behind about 10 seconds for what's actually happening. So let's fast forward, or let's skip to the actual what's happening right now. And now we're back up to looking at live data. Now, to illustrate this more, I'm actually going to save this recording. Let's save this recording and let's go open up a sample recording in Chanalyzer. So to save it, I'm going to click File and click Save As, and we'll just save it to the desktop. So we'll just save it as recording. So I'm just going to save it to my desktop here so we can come back and open this file up later. And now that we've saved this recording so we can come back to it, I'm going to go visit the Learn tab. And I'm going to click on recordings. Now, if you don't have a Wi-Spy, if you're watching this webinar just to kind of evaluate this and see if this is a product that you want or don't want, you can actually follow along here. If you were to download Chanalyzer 5 from metageek.net/downloads, you can click on the Learn tab and go to the recordings tab here, and you can open up these saved recordings. So feel free to do that. Feel free to do that after the webinar if you'd like to play with the software a bit more. So what I'm going to do here is going to go to the top one, 802.11b and G throughput testing is what this was. I was doing 802.11g and 802.11b throughput testing at home to show what Wi-Fi looks like in the spectrum. Since we looked at a non-Wi-Fi device before, let's take a look at a Wi-Fi device and see what that looks like. Now, this is where the waterfall navigation is really, really cool because we can see the entire recording from start to finish now. This isn't live data. This is a saved recording, so we're not adding any more data to the top, but we can navigate throughout this recording. And we can see that there were several events that occurred here. So let's check those out. We can change the time span that we are looking at by dragging these two navigation endpoints up and down. So I can actually drag them to this point in time. And I can even change the time span, the amount of time that we are looking at out here in the overview pane by dragging these two navigation endpoints individually. So I can kind of tune it in there. And now we can see that we are looking at exactly 51 seconds. We can change that time by clicking the plus and minus buttons here, but right now we are looking at exactly 51 seconds. So what happened here during this 51-second portion of the recording? Maybe we can drag it back a little bit and let's play it back while we talk about it. Well, what I did is I set up an access point on Wi-Fi channel 11, and I allowed it to use all 802.11g data rates, and I ran a throughput test on it. Just with a tool called iPerf, I ran a throughput test across the network to see how quickly we can move some data across. And we can see that during that throughput test, it made this flat tabletop shape with shoulders down each side. That's what 802.11g and also 802.11n look like in the spectrum when they're moving data. We can see what 802.11g actually looks like. Now let's skip ahead. I've got a portion up here where I switch down to channel 1, and I have a different network down there. I have a network that's set up to allow 802.11b data rates, so 1, 2, 5.5, and 11 megabits per second, those legacy data rates. And I did the exact same thing. I streamed, or I ran a throughput test. I moved a bunch of data across the network to see what 802.11b looks like. And we can see that instead of this flat tabletop shape, it makes a curve shape in the spectrum. And that's because it uses a different type of modulation. So the RF energy looks different in the spectrum. So we can see how different that shape is. Now, let's say that you see this shape in the spectrum and you didn't attend this webinar, so you have no idea what that is. You're going, whoa, there is some interference there, and it's bad. I can see it's red. It's talking a lot. We can see it's pretty consistent in the waterfall view. I need to take a look at that. I need to figure out what this thing is. Well, we've got a way for you to do that. If you click on the Interferers tab, this is a library of common signatures that you might see in the spectrum. A whole bunch of things that we figured that you'll probably run across in the spectrum at some point in time while you're using this tool. So you can actually click on one of these. You can go through and you'll go, okay, it's definitely not an AV transmitter. It looks nothing like that, but it looks a lot like this 802.11g/n signature. If you single click on that and then hover your mouse in the density view, then we can see, and normally it would follow my mouse around, but because I'm running my GoToWebinar software, it keeps it from following it around normally. But you can make a comparison. You can go, hey, you know what? That looks a lot like an 802.11g or n signature. That's probably an 802.11g or n signature. We can do the same thing with the 802.11b shape. If we click on this and hover our mouse up here, we can make that comparison and go, hey, that looks like that's an 802.11b or g signature. So if you see something in the spectrum that you don't recognize, use the Interferers tab and go take a look and see if you can figure out what that device is. Now, since these are specifically Wi-Fi devices, there's another way that we can detect these as well. like I mentioned earlier, Chanalyzer not only uses the Wi-Spy to get the spectrum analysis data, but we also use your wireless adapter. Now, in this case, since I'm running this in a virtual machine on a Mac, I'm using a USB wireless adapter, but you can use just your internal wireless adapter on your computer. So that's going to pull in the networks table. And these are all of the wireless networks that our wireless adapter could hear during the course of this session that we took. So I'm actually going to filter this out. I'm going to filter everything with 802.11 in it. I named two networks, 802.11. And so now we can see that we've got those two networks selected here. There's one called 802.11g, and it's on channel 11. We can see its signal strength, negative 28 dBm. That is really, really close. I was right next to it. And we can see that its maximum data rate was 54 megabits per second. Then we've got another one that I called 802.11b, and this is an old Linksys 802.11b access point, or old 802.11b home Soho router rather, and it has a maximum data rate of 11 megabits per second. And if we click on the display selected networks button, it'll actually show us where those networks are. It overlays the Wi-Fi data onto the spectrum data. Pretty cool, huh? So we can see that our 802.11g network is right here, and we know that's probably the same one because the heights are very, very similar. And we can also see that we've got an 802.11b network right here. Now, here's one thing I want you to notice. Notice that whether we're seeing a whole bunch of activity in the band or not, the network's always there. It's just when we start seeing a lot of activity that we actually see a signature develop. When you see a signature show up, I've had a lot of phone calls from people and they say, wow, I'm seeing all kinds of interference. Well, maybe it's not interference. Maybe it's just your wireless device. So think about that. And you can use this feature to make a comparison and see whose network is whose. Notice that what we do here is we draw a square for the 802.11g and 802.11n networks, and we draw a curve shape for our 802.11b networks, which is pretty helpful for giving a quick identification for what type of modulation you can expect those devices to use. And the last thing I want you to notice is notice how we alternated channels. If I select like a 3 or maybe we'll hit a 5-minute time span and I look at a large time span, we can see in the waterfall view where we ran on channel 1 and then we ran on channel 11 and then back on channel 1 again. You can use the waterfall view to kind of keep an eye on things over time. And that's something that we want to do. So now let's go ahead and open up our recording that we saved earlier. I'm going to click open, and I'm going to click on we named it recording. I'm going to open up that recording, and let's take a look at this recording to see what happened. Now, a recording file contains sessions. A session is kind of like a folder inside the recording, and we can have just about as many sessions as we want. So we can see that we had our full 2.4 gigahertz band one here. I can click on that. And we can see that this is when we first opened Chanalyzer, and we can see that for a while, we had kind of a period of nothing. Nothing happened here for a little while. We'll get rid of my filter there. We can see that nothing happened for a little while, and then we can see that we started having some activity here. We saw some activity starting here on channel 5. That's when we turned that non-Wi-Fi device on, that interfering device. So let's see if that's going to interfere with our wireless networks. Now, our network here is called, can anybody guess what our network is called here? It's called MetaGeek. Big surprise. So I've just filtered out the MetaGeek network. Let's see if we can get any here. Okay, there we go. There's our MetaGeek network, and we've got it grouped by ESSID. So we've got all of the access points with the name MetaGeek are grouped together. We can switch to radio grouping. So here's all of our individual access points. But if we switch back to ESSID mode, we can see what channels they're on. And we've got networks that are on channels 1, 6, and 11 in the 2.4 gigahertz band. We've also got a bunch in the 5 gigahertz band. We've got a good, robust 5 gigahertz network here. So even though I'm doing this testing, it shouldn't knock out our network completely. All of our 5 gigahertz devices should be fine. But we can see that we've got reception, we've got an Open Meeting 2, Open Office 3, and Open Meeting 1. So let's say that we wanted to give this data to somebody as a deliverable. Let's build this as a deliverable. So I'm going to click on Report Builder and click on New Report. And that's going to open up this brand new report in a new window. Now, even though we're on a pretty small screen, this is really fun on a big screen. But I'm just going to snap these to the sides, and we'll make the windows a little bit bigger to make it easier to see. But now we can switch back and forth between our Report Builder and Chanalyzer. So let's export some data. I'm going to hide color by utilization, and I'm going to hide display current trace. So we're only going to show our wireless networks. And I'm going to click Report Builder. I'm going to click Add Density Graph. Now notice what that did over here. It added a graph to our report. So now we've got a graph showing where our wireless networks are. Now let's hide the wireless networks and let's just show the density view. Let's show how busy things are here. And so you can do it here too. I'm gonna click Add Density Graph. So there we go. Here's what things kind of looked like in the spectrum. Not very busy. Things were looking pretty good. And then let's show what happened when we turned on this non-Wi-Fi device. So let's hit Report Builder and click Add Density Graph again. So there we go. Now we've got a block showing where our networks are, what things looked like before, and what things looked like when we turned this non-Wi-Fi device on. Let's also show a waterfall of how often it was talking. So we'll just look at, let's select like a 5 minutes is a bit extreme. Let's do a 2-minute time span. And let's send this to the report builder as well. Add density graph. Whoops, I added the density graph instead of the waterfall view. I didn't mean to do that. So let's just get rid of that extra one by just clicking the X here. And we'll hit report builder and then add waterfall graph. There we go. That's what I was looking for. So now we have a waterfall showing how often, how consistently this thing was talking. Now let's skip ahead to our final session. And let's select a 2-minute time span here. That's about all we have. This was a pretty short session. And we can see our wireless networks here. Let's hit Report Builder and click Add Density Graph, and we're done. But you know what? There's one more thing I want to add. I want to add this table of all of our access points. So I'm going to hit Report Builder and add networks table. There we go. Okay, so over at our report, let's take a look and see what we have added to this report. So we've got our first density graph showing where the networks are. And maybe I don't like the text in here, so I'm just going to get rid of the text, and I'm going to say networks. So this is where our networks are. This is all customizable, but I just got rid of the text because I don't need it. And now we've got a density graph. I like the text that's in here, so I'm going to go ahead and leave that alone. So let's change this one, density graph. Let's say interferer. Okay, so now we've customized that, and let's go to our waterfall graph. Let's leave that alone. It's totally fine. And then we've got our last one here. After unplugging the interferer, let's say after unplugging interferer. Okay, perfect. Now the last thing that we've got here is our networks table down at the bottom. So this is a table of all of our wireless networks. But you know what? There's one more thing that I want to get in here. I actually want to make a change to the waterfall graph. I'm not quite satisfied with what that looks like. So let's skip back over to Chanalyzer. Whoops, let's try it, snap. One question from Keith. If we use Mac and VMware Fusion, is an external wireless adapter required to get the wireless networks into the VM? Yes, it is, Keith. And that's because OS 10, Mac OS, just doesn't pass through the raw Wi-Fi data that we need. It passes it through as an Ethernet adapter. We only get Ethernet-like traffic. So we need Windows to be able to access a quote-unquote real Wi-Fi adapter. And in our case, pretty much everybody here at MetaGeek, we're all on Macs. We just use a USB Wi-Fi adapter. The Cisco Linksys AE1000 is like $9 on Amazon Prime. That's what we use, and it works great. So that's how I'm getting that Wi-Fi data. You can also just function without the Wi-Fi data if that works as well. So I hope that answers your question. So let's say I want to make a change to this waterfall. I'm not super happy with what that waterfall looks like. In fact, I want to utilize a feature here. I want to utilize the note feature. I'm going to click this button here to add a note, and I'm going to say interference started. And we'll say this is when the device started transmitting. And if we had a picture, we could add that here as well. You can use the notes feature to say like, oh, this is when I walked into a specific room. I'm going to fine tune where this is a little bit. I'm going to put it right there. You can use the notes feature for all kinds of things. And you can look at all of your notes over here in the notes tab. So here it is. We can even jump to it if we want. So now I'm actually going to go back over to my report builder. And I want to update my waterfall graph because I want to show that line there. I want to show where that started talking. So now we have updated that. And so now what we can do is we can do a few things with this. We can save this report to come back and open it later. Maybe we want to use it as a template. I have a training template that I use all the time. It's got some blocks in there with customized text. And then people send me their recordings. And then I go through and say, well, here's what I found. But I preface that by giving them some training templates. So you can save the report to edit it later, or you can export this as a nice PDF. You can also copy any of these graphs and tables out. If you click the copy to clipboard button, like this one right here. So now that is on my clipboard. We can open up an image editing tool. Like, this is totally pro, by the way. This is a professional tool, MS Paint. I hope you've used this before. We can paste this in anywhere we want. The tables paste in is CSV, so you can paste them into Google Drive or Excel or whatever you need to do, so you can get that data out to manipulate it. The report builder feature is an add-on. It may or may not be included with Chanalyzer, depending on what you purchase. Just look for something saying that the report builder accessory is included. Okay, so now that we've had a chance to really go through Chanalyzer and get an in-depth look at it, I want to take the last few minutes of the webinar, and I want to take a look at some common interferers that you might see in the spectrum. The first one that I want to look at is 802.11b HRDSSS. Now, this is probably going to be, you're probably going to be pretty familiar with this one already. We looked at this one earlier, and this stands for high rate direct sequence spread spectrum. Don't worry, that won't be on the test. This is an older data rate like 1 or 2 or 5.5 or 11 megabits per second. So this is all those older data rates. This is what 802.11b looked like. It makes a curve shape in the spectrum with these lobes down each side, just like we saw in the recording earlier. Next, the more common one that you're going to see is 802.11g/n uses ERP OFDM, orthogonal frequency division multiplexing. And the spectral mask, the normal shape that we expect it to make, is this flat tabletop shape with the two shoulders down each side. I'm going to try to fix that top bar really quick here. That's bugging me. So just take me a second. It's kind of like when somebody brings up a YouTube video and they leave the mouse in the middle of the screen and it just drives you crazy. That's what that top bar was doing to me. So I'm sure some of you can relate. Okay, so let's go ahead and jump back in and look at what ERP, OFDM, orthogonal frequency division multiplexing, what it looks like. This is the spectral mask. This is the normal shape that we expect it to be. The 20 megahertz wide channel is right here, but we're just going to accept that these lobes on the side, those are completely normal. So this is where our 20 megahertz wide section is. This is where the data subcarriers are. And this is just noise created on the side, but it is completely normal to see that. This noise right here, this is why we don't put access points super, super close to each other. I've seen some deployments where people put access points right next to each other, like within 10 feet of each other. And here's what happened. We had our data subcarriers right here, and then we had our access point right next to it, but it was swimming in all of the noise from the one next to it, and they were spilling over each other like this and causing problems. That's why we don't want to put access points too close to each other. When this screenshot was taken, I was very, very close to the client that was generating that activity. We can see our signal strength is about negative 55 dBm. We are very, very close to whatever device is generating that activity. Next is 802.11a, and this is where OFDM actually came from. Remember, 802.11a was the first 5 gigahertz standard, and we can see that it makes that same flat tabletop shape with the shoulders down each side. It's the exact same modulation scheme as 802.11g and 802.11n. And in this screenshot, this one's kind of fun because we can see that there's an 802.11a network here on channel 56. So the question here is, which channel is best? Which channel would we choose to deploy a new wireless network? We can see that there is 802.11a activity on pretty much every 20 megahertz channel across the band, except one. Right here, channel 132. There's nothing there. So if I was going to deploy a new wireless network, that's the channel that I would do it on. Typically, you don't see 5 gigahertz that looks quite this crazy, but if you ever get a chance, open up a spectrum analyzer at like a stadium or a conference or something like that, and typically you will see that it looks very, very busy like this. And this is what a 40 megahertz 802.11n network looks like. 802.11g used 20 megahertz wide channels, which were about that wide. 802.11n introduced double width channels, or 40 megahertz wide channels. So now they are twice as wide. Basically, instead of a 2-lane highway, we now have a 4-lane highway. These work awesome in the 5 gigahertz band, but in the 2.4 gigahertz band, do not use 40 megahertz wide channels. No 40 megahertz wide channels in the 2.4 gigahertz band, because there just isn't enough space. It all goes back to that talk that we had earlier about channels 1, 6, and 11. This is what a Bluetooth device in discovery mode looks like. Bluetooth devices work by, when you pair two devices like my phone, I have a Pebble smartwatch here on my desk. When you pair two Bluetooth devices, they pick a pseudo-random set of channels and they rapidly hop across those channels in a predefined pattern that they decided on. And so this is known as a frequency hopping spread spectrum device. This is a device that hops all over the place. And this is a device that is in discovery mode. So it's looking for other Wi-Fi devices. And we can see that it's making a whole bunch of narrow spikes across the band, a whole bunch of individual spikes. And I know that this is all the same device talking because the height is uniform. The amplitude is uniform across the band. Now it's hopping so quickly that we don't see the pattern, and the pattern is complex enough that we don't see that pattern in the waterfall view, but this is simply hopping on a predefined pattern. Now, typically our class 3 devices, like our phones and our tablets and our smartwatches and things like that, those devices have such a low output power that you typically don't see interference from Bluetooth devices. But class 1 devices can be very, very powerful, and they can cause problems. They're just quite a bit more rare. You usually only see them in specialized manufacturing environments or things like that. But that's what a Bluetooth device looks like in discovery mode. Here's a slower frequency hopping device. This is a baby monitor, and we can see that this device is hopping from channel to channel, much like Bluetooth, but a lot slower. We can see that it hung out on channel 5 for about 4 seconds, and then it moved over here to Wi-Fi channel 9 for another 4 seconds or so, and then it hopped all the way down here to Wi-Fi channel 1. Now, something very, very bad happened there. This device made a poor channel decision, because what's going on here on channel 1? If you look very closely, there is an 802.11g or 802.11n device or N network here on Wi-Fi channel 1. We can also see it in the waterfall view as well. And this device made a poor decision and hopped down on the same channel. Typically, you're going to see non-Wi-Fi devices make poor decisions like this. They don't make these decisions intelligently, and that's why analog devices are slowly kind of going away. We're kind of seeing less and less of them over time. Now, here's a fun one. This is an analog video transmitter. Makes a very, very distinct 3-spike shape. And this is a great example of how color is used in the waterfall view, because we can actually see those 3 spikes by looking at the color in the waterfall view. I was talking to a customer who does professional filming with quadcopters, which many people would call a drone. And he noted, he was like, oh, okay. He said the waterfall view is kind of like looking down on the density view. I was like, that's exactly it. It's like having an aerial view down on the density view. Now, these analog video transmitters, these are nasty, nasty devices. Notice the intensity of the color. It is red, which means it is talking constantly. It is a non-relenting transmission. These devices will absolutely kill a wireless network, just like the non-Wi-Fi device that I was using earlier. And this is an interesting one. This is a wideband jammer, and this device's purpose is to basically flood the 2.4 gigahertz band with activity and ruin everything. Now, you don't see these in the wild very often, and you really shouldn't, because they are definitely not legal. And I've only heard of these being used by college students. I heard a story where some college students used one to lock everyone out of the dorms. The dorms had 2.4 gigahertz locks, and so they enabled their jammer and nobody could get into the dorms. I've also heard, I don't know whether it was the same group or not, but I've also heard of these being used to get out of exams where that revolved around a Wi-Fi clicker, and they enabled this and it brought the wireless network down, so they couldn't proceed. They could not proceed with the exam. These are definitely not legal, and if the FCC catches you using one of these to bring down someone else's network, there is a hefty fine in the works. So you definitely would not want to use a device like this. Now, this is a fun one. This is an infrared motion sensor, and they're often kind of a random assortment of little spikes like this, a whole bunch of little spikes everywhere. These are those little devices that sit in the top corner of a room, those little devices that are, usually about 10 centimeters wide and maybe 30 centimeters tall or something like that. And they just watch for activity in the room at night. And when they see activity, they trip a security system. These are not very common in the US, but I understand that they're pretty common in Europe. This is what an Xbox 360 controller looks like. It's a lot like Bluetooth in that it's a frequency hopping device. We can see that the amplitude is the same across the board, and we can see that it's hopping all over the place. We can see all these little hops. Now, the funny thing about these Xbox 360 controllers is that you'll see this activity even when your Xbox is switched off. Your Xbox is constantly sitting there watching for one of the controllers to come on so it can power on the Xbox. Now, notice the intensity of the color. It's blue. It's like a little clap here and there. It's a little clap here and there. This device isn't like an air horn. It's not blasting the spectrum with activity. So in my experience, these typically don't cause problems with the wireless network, especially if you're just at home and you have one Xbox and one wireless network. It's typically not a problem. Although I did see a problem. I got an email and a recording from a very, very large Xbox 360 developer. They're developing probably one of the most famous Xbox 360 games at the time, and they had about 200 Xbox 360s all on the same floor for all their game developers, and the 2.4 gigahertz band was useless. It was absolutely flooded because of all those boxes sitting there waiting for a controller to turn on so that they could power on. So that's definitely something to watch out for. This is what wireless headsets look like. We can see that they like to talk pretty consistently. They don't really move around. They like to stay on the same channel. And these are going to cause problems for anything that's on Wi-Fi channel 6 or Wi-Fi channel 1. It's going to cause problems for any of those devices. So watch out for things like wireless headsets. And be sure that when you go on a site and you're asking them, hey, do you guys have any non-Wi-Fi devices? Be sure to open a spectrum analyzer and actually look, because a lot of times, the customer will say, oh, no, we don't have anything wireless here, when really there are some things like wireless headsets, things like that sitting around that you're going to want to watch out for. If you want to download Chanalyzer 5, metageek.net/downloads, even if you don't have a Wi-Spy, you can download it and you can open up those sample recordings. And you can check out the software. You can build some reports and play with it and check everything out. And if you have any questions, this is a great time to ask them. If you would like to ask the question off webinar, feel free to contact me at support.metageek.net. Just open up a support ticket. I'd be more than happy to answer your questions for you. One question I have is, can I talk about the tools and the toolkits available as packages? Yeah, Richard, that's a great question. So let me just grab a web browser really quick here, and let's take a look at some of some of the kits. We bundle everything. Everything at MetaGeek is kind of offered as bundles. Question from Gerard is, does it work in the 5 gigahertz band? Yes, it did. Unfortunately, I didn't have time to demo that, but you can switch to the 5 gigahertz band, and absolutely the Wi-Spy 2.4x, which is this one right here, 2.4x is 2.4 gigahertz only. And the Wi-Spy DBX, DB stands for dual band. That one works in both 2.4 and 5 gigahertz. And Chanalyzer kind of comes in a modular way. You get Chanalyzer 5, and then you can add things like the report builder. We used that to build a report. You can add the device finder, which is that directional antenna. There's the lab accessory. This is kind of designed for hardware engineers and scientists. And then there's also the Cisco Clean Air accessory, which you can use to connect to a Cisco Clean Air access point. And we offer them in a variety of different bundles. And you can also purchase those accessories separately for about $150 a piece. You can purchase them with it as a bundle, or you can purchase those after the fact if you'd like to add them later. And a question from Robert, will this webinar be available for download or email delivery? Yes, it will. If you'd like a copy of the webinar, go ahead and contact me at support.metageek.net. Just let me know that you'd like a copy of the webinar. I do plan on posting this in our knowledge base here within a week or so. I'm hoping to do that very soon. All right, if there aren't any more questions, then I think we should go ahead and end the webinar. We're right at about an hour, and I forgot to mute my phone. We're right at about an hour here, so let's go ahead and end the webinar. If you have any more questions, feel free to contact us. Thanks for attending. Everybody have a great rest of your week.